This objective is about explained and unexplained variation and the least squares regression line. So there's a lot going on here, so I just want to kind of take a second to break down what's happening. So we have a scatter plot of our data. We have an equation for our regression line, or our line of best fit. And over here we have the sample data, x values and y values, that are plotted in the scatter plot. And then we have a series of calculations. So the first thing I want to draw your attention to is the fact that the order of these columns in this calculation table change with every problem. So you cannot just memorize that this first column is, for example, the regression sum of squares, and the second column is the sum of square error, and the third is the sum of squares total. You actually have to understand what these heading rows mean at the top of this chart. So I want to go through that with you. In this case, y is your observed values minus y hat are your predicted values. So basically what we're trying to find is how far off are our predicted values from the ones we actually observed in our data. And together, these represent the sum of squares error, right? So how far off, how wrong are we about our predicted values from our observed values? So we'll label this column sum of square errors. In the next column, we have y hat minus the mean of y. So we have our predicted values minus the mean of our observed values. In this case, this represents the sum of squares of our regression line. And then lastly, we have our observed y minus our mean of y. And this should look familiar to you from all of our other calculations, where we're taking our y values minus our mean of y, and this is helping us to get at the variance within our data set. Right? And so this is overall our sum of squares total. Another way that you can tell which one is the sum of squares total is to see which of the three numbers is the largest, because the sum of squares total is equal to the sum of squares errored plus the sum of squares of the regression. Okay, another way to verify that you're on the right track with identifying each of these columns. So if the sum of squares total is the largest number, the smallest number should be your sum of squares error. A least squares regression line reduces the amount of error in your calculations. That's why it's called, so the process of least squares actually minimizes the error that you're making. And another term for the difference between your observed y and your predicted y is a residual. A residual represents the amount of error you're making with your predictions versus your observed y values. So we should always be minimizing our residuals or our error when we're calculating a least squares regression line. So this column, the regression or the sum of squares error, should have the smallest value, the sum of square total should have the largest value, and then the one in the middle is your regression sum of squares. Okay, so keeping all of those things in mind, let's let's look at our questions. So the first one says, for a particular data point that we have, what is the value of the residual? So again, the residual equals observed minus predicted, or y minus y hat. And in this case, we've been given an x and a y value. So our x value is 214.9 and our y value is 211.1. And where do we get our predicted y value from? Right, the regression line is going to give us predicted y. So it's our observed y minus negative 9.78 plus 1.06 when x is, over here it's given to us, 214.9. Okay, so we can calculate this as 211.1 minus 218.014, which is equal to negative 7.014. And we want to round to 2 decimal places, so negative 7.01. Question number 2 says the variation in the sample y values that is not explained by the estimated linear relationship between x and y is given by, and it's asking which of the columns, the total sum of squares, the error sum of squares, or the regression sum of squares, which for these data is, and then you have to give the value of the column that you think corresponds to it. So it's testing your knowledge of the definition of each of these sums of squares, and then it's asking you to pick out which one it is in the table. So in this case, the variation in the sample y that is explained by the linear relationship is the regression sum of squares. And so before we marked that that was our middle column in the table of calculations. So the variation that's not explained by the linear relationship between x and y has to be then the error sum of squares. And for our data, we already discussed, this is 935.7938. The value r squared, so moving on to number 3, the value r squared is the proportion of the total variation in the sample y values that is explained by the estimated relationship. So r squared is always the regression sum of squares, which in our case is 5279 point, I'll round your answers up, so we're going to go 5280.00. So we have y minus y hat is 211.1 minus 218.014, and this is equal to negative 6.914. And we're asked to round our answer to at least 2 decimal places, so negative 6.91. And the next question, they're asking us the variation in the sample y values that is not explained by the estimated linear relationship. So our regression sum of squares is the variation explained by the estimated linear relationship. And so the residuals, or the sum of square of errors, is the amount that's not explained by the linear relationship. So our error sum of squares, and in this case, as I already pointed out to you before, is the smallest of these values, which is 935.7938. Moving on to question 3, the value r squared is the proportion of the total variation in the sample y values that is explained by the estimated linear relationship. And for these data, the value of r squared is equal to. So in order to calculate r squared, r squared is equal to the regression sum of squares divided by the sum of squares total. So for us, our sum of squares for the regression is 5,279 in sum, divided by the sum of squares total, which is 6217.2520. And this is equal to 0.8492. This number should always be less than 1. And in practice, it is hardly ever this high. We're never so good at estimating our variation. Okay, but in this case, round our answer to at least 2 decimal places is 0.85. This means that 85% of our variance in the data are explained by the linear relationship that we've estimated. And then question 4 says, the least squares regression line given above is said to be a line which best fits the sample data. So getting you to think about, what does this mean? The term best fit is used because the line has an equation that minimizes the error sum of squares, which is 935. Yeah, I didn't sound very confident about that, did I? But in this case, yeah, the line of best fit is minimizing your residuals or your error sum of squares. So don't let ALEKS trick you like it almost just did me, right? Where I thought, well, that's already the answer to a question, so it probably can't be the answer again. It definitely can be, so don't let it fool you.